Hey everybody, this is Larry. This is day 9 of the Leetcode December Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem, binary search tree iterator. So usually I solve these live. I look at these problems for the first time, so it may run, or like I go over my thought process instead of going right to the solution. So yeah, feel free to fast forward, skip ahead, whatever you like, or run it on a faster speed. Okay, so today's problem is binary search tree iterator. Okay, yeah, just in order. Okay, this seems pretty straightforward. You should be able to figure out how to do it just by in order traversals. In Python, there's actually some syntax for recursive generators and stuff like that, so you could yield as you go through. But not actually familiar with that much. It's been a while. So I will probably do that later. But anyway, but the thing that I want to focus on, of course, is just the the algorithm and the implementation. And once you get the right idea, you should be able to implement it in different ways. But still, syntax is just syntax, right? So okay, n is 10 to the 5th. The numbers don't really matter, and you go through all the entire node. Okay. Yeah, I don't get this. Do they expect us to be slower? But okay. So basically, yeah. I mean, I think you can obviously just do an in order traversal in the beginning and then go through it node by node. But that'll be O of n instead of O of h, because you converted everything to a list. And yeah, you could do that. But I think that is not the spirit of things. So let's try to do it. So what I would do is just a regular in order traversal, but instead of an implicit stack by recursion, we can put it on a regular stack and just try to do it that way. Okay, so yeah. So okay, so let's just say we have a pointer to the root and we have a stack. Okay, and then this is just a lot of what I call bookkeeping, and bookkeeping is not an algorithm because I feel like apparently I use that term a lot. But it's just about keeping track, keeping your books in good place and just keeping track of where your books are, or in a book where everything is, right? So it's just about keeping track of everything and as much as you can and as efficient as possible. That's what I mean by bookkeeping usually. Okay, so. And bookkeeping is an English term, not an algorithm term. Though some people, so it does come up a lot because it is something that comes up a lot for implementations. Okay. So yeah, if okay, hash next. Maybe we just do if self.current is none, something like that. And then now, okay, let's say we have this. How do we want to? Give me a second to think about how I want to do it. I mean, we have this. I haven't done the iterative version of the recursion that much, but I guess we can. I'm thinking of just whether like we should start from the current or we kind of just go all the way to the left, which is how we would go. So maybe I do it this way. Let me play around with that and we'll see. So well, self.current is not none. Maybe we write another way. Yeah, that's okay. Yep. And self.current.left is not none. Then self.stack.append, self.current.left. And self.current. Okay, so I think this is okay actually. Let me tighten this up code. Okay, so basically now for the beginning of the node, while it's not none, we append the left and then we go to the left, right? So that just eliminate the left in order. So then now next, so this is actually not true. And length of the stack is greater than 0. Because if the thing's on the stack, then we could pop it, right? So okay, so next, what does that mean, right? So if the self.current is none, we set it to, we pop it back to the stack. So if self.current is none, if I mean, we assume that there's going to be a oh yeah, there we go. You may assume that otherwise you may return like an error or something. That's why I wanted to check. Okay, so if self.current is none, then we what happens, right? Well, we definitely want to pop. So yeah, so self.current is equal to self.stack.pop. So then now we return self.current. Yeah. Otherwise, well, let me think for a second, right? Let me think. So what I'm thinking right now is about what I call the invariant, and algorithmically the invariant of the states as I move through them and try to figure out what state changes and what haven't changed, right? So basically we have all the left of the states. So I'm just trying to visualize in my head how to proceed forward, which is that, okay, so we have all the left, if current is none, we pop up, so then now the current is one higher, right? So we do want to return this, but then now we want to also put like now we have to process the right real quick. So okay, so self.current is not none. That means that we just processed it, and if we just processed it, then we process the right? So if self.current that right is not none, then we want to push self.current.right, or maybe, well, self.current is equal to self.current.right, and then we go all the way through the left side, right? Kind of similar to this. So then yeah, well, self.current is not none, self.stack.append self.current, because basically we just process everything to on that node. And I think in my mind maybe this is good. I mean, there is going to probably be some edge cases, but in my mind this is close. So that's kind of let the code visualize what we have right now. Okay, and also obviously apparently we return the node instead of the answer, so that's fine. Yeah, so let's return that. And apparently we're still not right, obviously, because we're missing some cases. So okay, so after we pop, what happens? Oh, so after we pop, okay, so let's just do while you use. I think we're missing a state. So after we pop, we have to okay, so after we pop, we actually process the right side, right? So is current always going to be none? Do we need current? Maybe my current is just confusing me a little bit, because it doesn't seem like I use it anywhere. So okay, so let's just get rid of this context then, so that it's less confusing. Because then now the entire state is just based on self.stack, right? So then now we don't need any of these. as I said, I'm exploring it with you, so apologize if this code is suddenly crazy. But okay, so basically, we always take from the top of the stack because we always assume it's true or valid. So this is the value that we're going to return at the very end. But then before that, we want to do if current.write is not none. That way. Oops. Definitely very rusty on the on this order of it, but that's okay. Did I miss somewhere? Oh, whoops. A little bit rusty on the non-depth first search implementation, but okay. So after we cleared it up, I think I had, so my initial idea, my initial implementation idea was just having a pointer that points at the current thing. But I guess, but the reason why I kind of changed my code halfway through, oh, let me submit it, because one time I forgot to submit and I just forgot to submit for that day. Cool. But yeah, so, you know, definitely think through your states. Sometimes, as you can see, my initial idea doesn't make sense on the implementation side. Some people think it ahead and plan everything out before they code. I do a little bit of both, a mix in between, because I like to visualize with my code as well, which is what I do when I run the code. But anyway, so instead, because I was thinking about having a pointer that points at the tree as you move along, but instead that actually ends up being, I was like, okay, actually you could use the top of the stack as the pointer. So that's basically why I changed everything as a result. But yeah, going through the code, and this is, I guess, textbook E or close to it. An explicit stack implementation of depth first search, and basically what I do is that I go down the left as I can, because when you do a depth first search, or sorry, when you do an in order traversal more specifically, you know, you always go to the left as far as you can before you process the current element. So this simulates that, this as well, and then here is when you get to the next, you process the top of the stack, and then you go to the right because that's what you process, and then you recursive done that. You could have also maybe you know, refactor this, and probably should have, to kind of make this more clear into one function. But yeah, so what is the complexity of this? So you may, you know, a naive analysis of this code would be like, okay, well, there are while loops on each function, and this could be O of n, so this is n squared, right? But it turns out that this is actually, the entire thing is O of n, because if you look at this, this while loop only happens for each node once, meaning that each node will only be pushed on the stack once, right? Because there's no way to go through each node multiple times, at least not with this implementation. So it's going to be linear time, and because you have linear number of cores, on average, each core is going to be O of 1. And that's where sometimes you hear the term O of 1 amortized, and that's what that means usually. In terms of space or memory, you know, we put everything on stack, and you only go as, the stack gets only as big as the height of the tree, because, well, you pop them off as you go otherwise. So that means that, yeah, this is going to be O of H, or for the worst case for the memory. That's all I have for this problem. It's annoying, but it's good practice to kind of practice what you haven't done before, and I haven't done this before, because usually I just do it recursively. But it's been a long time. Cool. Let me know what you think, and I will see y'all tomorrow. Bye bye.